Welcome to the second lecture video in the Class 22 series of lecture videos. We ended the first lecture video talking about different potential products for an E2 reaction, whether our reaction was under thermodynamic control to give the more stable alkene product, or whether it was under kinetic control, in which case the reaction with the lowest activation energy would be the reaction that would be preferred regardless of whatever product that was produced. So here we have a review of that. Here we've got sodium methoxide, which is, a fairly slender, strong base. We could, of course, do an E2 reaction where we pluck this hydrogen off of this tertiary carbon. That's a tertiary beta carbon relative to the alpha carbon, which is bonded to our tosylate leaving group. Or we could pluck a proton off of this methyl carbon, which is another beta carbon. I've labeled it beta prime. And if we're under thermodynamic control, we're going to prefer to have the more substituted alkene, which arises from plucking off the hydrogen bonded to that tertiary beta carbon versus a hydrogen on this primary methyl carbon, which is labeled beta prime. What is pH? pH stands for phenyl. It's like a benzene ring. And if we followed our geometry for the E2 reaction mechanism, where the hydrogen on the beta carbon is antiparaplanar to the tosylate leaving group, we get this Z alkene. This is a different isomer, and again we're plucking the tertiary beta carbon hydrogen off, and in this case we're producing an E alkene. How about E1? Well, E1 will generally produce the most stable alkene, and we ask why. Well, it's under thermodynamic control, and there is reversibility for E1 reactions. So we tend to sink to the most stable product, which in this case would be a tri-substituted alkene versus this di-substituted alkene. And by reversibility, what I mean is our alkene can be protonated and again form a tertiary carbocation by this strong acid, and that's actually the next reaction that we're going to look at for alkenes. We're going to look at Markovnikov addition of strong mineral acids to alkenes. So here we go. Markovnikov addition. Here we have cyclohexene, and we add in concentrated hydrochloric acid, and we get chlorocyclohexane. So how did we accomplish this electrophilic addition? Well, it's the last step of E1 in reverse. So we protonate our alkene, form a carbocation, and then we do SN1, our good nucleophile, our chloride anion, substitutes in with a lone pair of electrons into that carbocation center to give us our chlorocyclohexane. It's not a new reaction, like I said, just the last step of E1 in reverse, then substitution. There are rules for asymmetric alkenes. So cyclohexene is a symmetric alkene. Here we have 1-butene. So let's say we add HBr. Well, we get all 2-bromobutane, and we would expect it to be racemic. We get no 1-bromobutane. So why is that? Well, when we protonate this alkene, we're going to protonate it in such a way to form the most stable carbocation. So that would be the secondary carbocation versus a potential primary carbocation, which we have said we will not see this semester. So for the purposes of our class. And then of course the bromide anion feeds into that carbocation. For Markovnikov additions, the group that is added, in this case the halide, goes to the carbon that forms the most stable carbocation. And of course, since your intermediate in these Markovnikov additions is a carbocation, you could potentially expect all sorts of carbocation rearrangements. We'll go ahead and review this and then dive into that in our next lecture video. Good luck with the question from this one in the meantime.